Welcome back, everyone. Right after the break, we have now a long session. It's almost 2 hours, but there's a good reward at the end. It's called beer. Yes. So, first presentation of this session is from Daniel Spierling from SwissIX about how to do DDoS mitigation there on the peering LAN. So, get on the stage.
Check, check. Mic is on. Alrighty. Good afternoon, everybody. I hope you enjoyed the afternoon break and the conversations which you had. I'm glad to be here. I'm glad to talk to you, and thank you for the opportunity. Arist, he reached out to me and asked if I would be happy to do a presentation on DDoS mitigation, which is available at SwissIX. And I gladly said yes. And Arist, he even sponsored a hoodie for me. So Arist, thanks again for that. As some of you might know me, but most probably don't, let me start with a quick introduction of myself. I'm working for DKIX, as you have seen on the first slide. I joined in 2011 as a junior network engineer in Germany. We have a dual study program where you can be at the university for half a year and then be at the company for half a year, and that took me like 4 years. So I was essentially working part-time at DKIX as a junior network engineer, and then decided to continue my networking journey for a couple of years, where I was working on the daily operation, on call, and everything which you would do running an IX network. In 2019, I then decided to move to the evil side, to the sales side, and support our sales team as technical sales engineer, where I work everything related to pre-sales for our peering products, where I help with all different types of topics around BGP traffic engineering, IIR validation, IIR security, do workshops, education, IXP development, and most recently, I mainly work as solution architect for cloud and enterprise products. The presentation today is about DDoS, and I want to start with a quick recap about DDoS, what and how. So DDoS, as we know, it attempts to consume a finite resource by exploiting weaknesses in design and or the lack of the underlying infrastructure. So it affects, in the end, the availability, which leads to a denial of service. There are a couple of DDoS attack vectors, and here are some of them. The first one being an application layer attack, which targets specific application instances and not particular the underlying infrastructure, for example, by raising a lot of HTTP requests out of a botnet towards a target. And creating an HTTP request is, from a computing point of view, perhaps pretty small, but to actually respond to that HTTP request, depending on the application, the server might need to get data from a database or engage other third-party entities, etc., to create that response. And if you send enough of these requests, the service will go down or might go down. Another attack vector are the protocol attacks, exploiting the stateful behavior of TCP. So from a botnet opening a lot of TCP sessions, and the server and also the devices in between, they need to open the TCP session after the first SYN packet and keep that session open, but the botnet would never reply and really finalize that TCP session. So it will consume all the memory or all the space available, and the application or the server might become unavailable. And last but not least, the reflection attack or the reflective amplification attacks, and this is what I want to talk about today. It exploits the behavior of unsecured NTP DNS protocols or servers, and can be executed rather easily. And the important thing is that it doesn't just affect the target, but there are also a lot of bystanders, and it affects the infrastructure in between. So how does that look like, or how could that look like? We see here on the left side an attacker which controls a botnet, and that botnet utilizes OpenDNS, NTP, LDAP, SSDP servers, for example, and sends requests with a spoofed source IP towards the server. And given that the IP is spoofed and doesn't belong to him, it's usually the IP of the targeted victim, all these servers will start responding. And the criteria here is that the request in comparison to the response is pretty small, and the response is way bigger. So I can amplify the attack on my targeted victim. As I mentioned before, there are a couple of bystanders who are affected by that as well. So it's not really the victim who is affected here, but perhaps the regional ISP or the IP transit carrier who needs to forward all that traffic towards the targeted victim. Traffic might be passing through different ways. And one of the ways is the IXP as well, which we want to look into more detail today. If we look at the protocols which are used as attack vectors, there can be multiple or different protocols leveraged. Some of the most commonly observed or used protocols is what I brought here on the slide. DNS, NTP, Chargen, Memcached was big in the news some time ago. And on the very right side, you can see the amplification factor, which each of these protocols, when the attacker is doing a reflective amplification attack, how big that amplification factor is. So these DDoS attacks, also known as volumetric DDoS attacks, they are on the rise since many years and really becoming a problem and becoming bigger and bigger. And NetScout or other researchers as well, they're always reporting on that, like what was the newest, biggest wave of a DDoS attack, right? So what can we do? What can we do about it? First of all, for everybody who is running a service provider network, don't be part of the problem. Don't be a spoofing-friendly network. There are best common practices available on the internet, which are helping with suggestions for network operators how to secure their network. And don't let any traffic in or out of your network that is not designated for or has not to come from your network. Proactively scan and remediate abusable services, etc., etc. Visibility. Visibility is key. If you don't have visibility, how should you protect your network or your customers, right? Another point is maintain enough total ingress network capacity into your network to ensure bandwidth, but also throughput. But of course, bandwidth is costly. Okay, so it can only scale towards a certain point which you as a company are willing to invest to have in total capacity in order to cope with these attacks. Deploy a commercial mitigation system. We have A10 as a sponsor of SwiNOG today. There are multiple vendors offering these on-prem solutions. Alternatively, there's a lot of cloud scrubbing providers available as well. If you decide that you don't want to mitigate a DDoS attack in your network, there's Akamai Prolexic, there's Cloudflare, there's F5, etc., etc. If you decide to mitigate DDoS up to a certain threshold, perhaps you define in your risk management that you want to mitigate DDoS attacks until a certain threshold before you then let a DDoS scrubbing center take over and protect and just return the clean traffic to you. If you do that, if you decide that road, you can use FlowSpec. You can use FlowSpec within your network, utilizing BGP to inject access lists or routing policies and filters, or to divert the traffic within your network, but also towards the providers. And last but not least, another example is the remote triggered blackholing. There's source-based remote triggered blackholing, and there's also destination-based triggered blackholing. And the destination-based remote triggered blackholing is what is available at SwissIX. SwissIX offers remote triggered blackholing towards its members. It supports the BGP well-known community, the BGP blackhole community, which is defined in RFC 7999. If we look at the picture, we see the attacked network, ASD, at the very bottom. And you see ASA is sending legitimate traffic, ASB and C are sending the bad traffic. And the traffic can be blackholed, meaning that it's dropped within the IX network, within SwissIX, which I have shown here in the diagram, and which I want to highlight and show you how it's actually done in the following slides. If we go to the looking glass of SwissIX, we have the option to search for prefixes, which are learned over all BGP sessions. But you can not only look for BGP session states and prefixes, but you can also search by BGP community. And this is what they did here on the screenshot, just to see who of the participant members as of today is already using the BGP remote triggered blackholing. And in the looking glass, you will see that these blackholing announcements, when I search for it, the results are marked with the little dark or blackholing symbol. And if I click on a specific prefix, then a pop-up appears, and then I will be able to see all the different attributes and also the BGP communities which are related to that specific prefix. And over here, we also see highlighted in black that the well-known BGP blackhole community has been set. So there are already some members using it, but how is it actually working? How is it implemented? And this is why I brought this example. We see, as an example, a hosting provider, for example, on the bottom left. On the top, we see 4 different peers. In this scenario, we also have the route servers available. So the hosting provider might send his routing information, his prefixes, which are available in his network, through BGP to the route server, and the route server redistributes these prefixes to the peers. In this scenario, then, the traffic is flowing towards our example member on the bottom left. But now let's imagine a DDoS attack arises. So we have 3 networks carrying bad traffic marked in red. However, we also have one other network or one other peer marked in green, which still has valid or legitimate traffic. And we see in this example, there is a server farm, and because of the DDoS attack, in this case, the link of that particular member might be oversaturated. It is causing a connectivity issue for his entire network or his entire data center. And this is where now the BGP blackholing can be used. Within SwissIX, we do maintain a specific host, which we call the black hop next hop host, which we now see on the bottom right. What our example member on the bottom left now can do is use the BGP community, which we saw earlier, the well-known BGP blackhole community, and send a BGP update message towards the route server or also towards the specific peers, with the IP address in his network being under attack, and which he now wants to have mitigated or the traffic dropped within the IX network. So he sends that BGP update message to the route servers. The route servers then detect that the well-known BGP blackhole community has been set. And before the route server redistributes the routing information, the route server will rewrite the next hop IP of that specific announcement to the IP of the blackhole next hop, which we see on the bottom right in black. This will therefore then lead to the situation that the routers trying to route data towards this specific IP, which is under attack, now is no longer the next hop of the actual owner, which is on the bottom left in blue, but that the routers which are carrying bad traffic towards that IP range are now trying to send the data towards the blackhole IP, because that has been rewritten by the route servers. And this triggers then the mechanism to actually blackhole the traffic, because on the ingress side of the fabric, we have MAC access lists which are looking for traffic which is destined to the MAC address of the black hole. So there's a specific entry in the MAC access list on the ingress side. Whenever there are frames to be forwarded to that destination MAC address, the frame is dropped. So this means that it is not even entering the fabric, but already being dropped on the ingress side of that member port. So this is how the remote triggered blackholing works. There are, however, some limitations to it. You can only completely drop the traffic. There is no analysis possible of how many traffic is being dropped or not, let's say a lot of insights into the dropped traffic. And if you want to see if the attack is still ongoing or not, and assuming the attack is just through the IX, you would need to deactivate it and activate it again to see if there is still bad traffic coming or not. So you need to turn it on and off. Another limitation is that it is very low in selectivity. It means you can drop the entire traffic or you can drop nothing. So lose it all or not. And if you drop everything, essentially the attacker has also achieved what he wanted. He made your application or server unavailable. And last but not least, it also relies on the goodwill of the peers on the internet exchange. Why? Because in the case of a /24, which is being blackholed, it's pretty easy because we all on our border routers, for IPv4, for example, we accept announcements as specific as /24. If, however, I want to blackhole a single host, a /32 IPv4 host, for example, and the route server is redistributing it to all the members on the internet exchange, that would require every member to accept the announcement, even though it's more specific, when it is marked with the BGP black hole community. But not all the member routers are supporting that. So it's not really efficient, and I have a graph for that in a second to make it a bit more clear. What we did at DKIX some years ago, we looked into that and thought, okay, how can we improve that and how can we make it more efficient for service providers to use that remote triggered blackholing possibility? And what we have developed is what we internally call the blackholing advanced service. And the blackholing advanced has some additional functionality. We now offer analysis of the traffic which is being dropped. So we provide to the members more insights into the bad traffic. It provides very high selectability. So you can black hole or have the IX fabric just drop specific transport protocols or specify certain ports. So basically you can combine layer 3 and layer 4 criteria to be dropped. It is implemented directly in the Nokia hardware, so it's filtering within the fabric instead of relying on the goodwill of the peers. And this is something which we are now also planning to enable and bring to the SwissIX fabric as well. The blackholing advanced is no longer really a blackholing, but more actually a filtering mechanism which is introduced into the IX fabric. Some might know it from BGP session calling, for example, when port 179, which is used for BGP communication, is being blocked in the IX fabric in order to have BGP session timers time out, basically. Yeah? Using this blackholing advanced mechanism, BGP session calling will be supported, or you can use it to mitigate attacks. There are over 60 predefined filters which members can use on the IX, and the IX fabric will automatically and dynamically apply these as QoS-based filters into the fabric. And how does that work, or how does that look like on the backend side? So on the very top, this is where it starts. We see the control plane and the different IXP members. Using BGP routing towards the route servers, this is the signaling process. So this means that over BGP, you can communicate towards the route servers using BGP communities that a specific prefix should be blackholed. In the middle, there is a blackholing manager. And then on the very bottom, we have the IX fabric, which then is used to actually update filters or program filters into the data plane, into the switching fabric. And how does that blackholing manager look like? Here, we zoom in a bit more to try to understand how it works. At the very beginning, it starts with an iBGP session from EXA-BGP monitoring hosts towards the route servers. And through that way, the EXA-BGP monitoring host is receiving the BGP updates from the specific members. The BGP message is then being parsed and processed, and all the commands to filter specific traffic is then put into a token bucket queue, and then through a network manager, which orchestrates the IX fabric, is then programmed into the fabric. If we now take a look, how does this advanced version compare to the standard remote triggered blackholing? We did a test setup. In this test setup, we created our own ASN, connected it to DKIX Frankfurt, announced IP space over the IX, and then went into the darknet and bought our own DDoS attack to attack our test system. And it is tremendously easy to actually do it. You just go into Tor, you bring a couple of Bitcoins, and then you can pick and choose which attack vector, how many hosts in the botnet, which attack size, etc. It's very easy, like shopping online, basically, how different hackers, let's say, make their botnets available to be used by others. So this is what we did. And you see here the overtime measurement, which we did. On the x-axis, you see the time. On the y-axis on the left, you see the size of the attack in terms of traffic, megabits per second. That is the red line. And on the right, you see the amount of peers in blue, where the bad traffic originates from, just from the IX perspective. So we started the attack and then started to use our standard remote triggered blackholing. And then we see that in the middle of the graph, the blue dots are reduced. This means that about 8 peers effectively accepted the more specific announcements, and the traffic was blackholed as I indicated and shown before. However, there are still peers who did not accept the very specific /32 announcement, so the traffic still kept coming. This means that the remote standard blackholing isn't always super effective. And if we compare that to this advanced version, where we program the quality of service filtering rules into the IX fabric, this is what we see here on the right side. The same test, just using the other mechanism. We can see here that first we use the BGP community to actually shape the traffic. So we picked an NTP reflection attack for our test. So we used the BGP community to indicate traffic shaping of NTP traffic to 200 megabit in this example. So we wanted to test the shaping, and you can see that the traffic, the red line, is being shaped exactly at 200 meg. And then at the end, we also wanted to test the dropping functionality, and this is what you see at the very right side in the dark gray area. You can see that the red line goes down to 0 and no more traffic is forwarded. This means that you can use these BGP communities, which will also be shown in the BGP looking glass, highlighted here as an example in black, where a rule is set to drop all UDP traffic with source port 19, for example. And these BGP announcements will then lead to this automatic programming of the cross-filtering rules, which we see here on the right side, into the Nokia fabric. Last but not least, my last slide. Currently, the service is available at DKIX, and we are planning to bring this also to SwissIX. We do maintain a PDF document where we show all the available BGP communities, where we document them, like which rules are available, what is the corresponding BGP community, etc. So that is seen on the left side if you're more interested in that. happy to share that through email, or perhaps later on during a break, we can look into that. And then on the right side, there is a Kibana dashboard, and the Kibana dashboard will give you all the insights. So how many rules are currently in place, how much traffic is being caught by each rule. You see the utilization of how much traffic is actually being dropped over a day. There's a Sankey chart showing the source and the destination IP in your network, and also a geolocation of where the abused servers of the DDoS reflection attack are geolocated. If you want, we can look into that in more detail as well. I can send it over through email, or we can look into that in our break as well. And that brings me to the end of my presentation. I would like to thank you for your attention, and would like to open the floor to questions if there are any.
Thank you, Daniel.
I have a simple question.
Not yet.
Confirms that it's off.
Very clever.
Now it works.
What would happen if one of my BGP customers do an announcement for 8.8.8.8/32 with your BGP attributes?
Very good question. So I forgot to mention that for these BGP communities, the route servers, which act as the interface, that we perform standard IIR validation and RPKI validation. So if your customer would not have the correct route object registered with write for 8888.0/24, or have a valid ROA for that, then the announcement would not be accepted, would be dropped by the route servers, and therefore also not programmed into the fabric. So that's one thing. And also, the filter is always on the egress side of your port. This means the filter will always be programmed into the IX fabric on the port which faces your router. So it's not applied overall in the fabric, but just, let's say, on your port on the egress side. Hope that answers the question.
It was the same question, please.
Okay, yeah, perfect.
The question I have is about the standard blacklisting, actually. You said if you want to know if the attack is still ongoing, you'd have to turn off the blacklist. But couldn't you just count the packets that are dropped?
You could. Currently, however, in the standard implementation which we offer, we are not exposing that to the customer in the portal. But in theory, yeah, you could look at the counter of that access list where the packets are dropped and see the increase of drops, and then show that to the customers, yeah. And then you would need to show that over time, and then at least you would have an indicator. Yeah, I agree. But usually the attack would come over multiple links. It would not just be on the IX. Perhaps you are connected to multiple IXs, or you are dual homed with 2 IP transit providers. So usually you would see that over there as well. The blackholing mechanism is not, let's say, the entire solution to solve all your DDoS problems. It's just, let's say, one tool in a toolbox of a service provider in case he wishes to use it. Yeah. Another question? Yeah.
Hi, Simon Leinen from Switch. The standard mechanism in BGP for transmitting fine-grained filters is FlowSpec, I think.
True. Yeah.
So did you consider that? And if so, why did you choose to use your own extended communities?
Yeah, very good question. So the idea of our R&D team was to utilize our bird route servers, which also actually support FlowSpec. But they looked into it, but they said BGP communities are, let's say, more common, or is something which everybody supports. Not all the members of an IXP are all able to use FlowSpec on their side. So they wanted in the first version use BGP communities because it's more readily available among the peers. And BGP FlowSpec is something which is on the roadmap and would be offered then in the future to solve exactly that. Yeah.
Last question.
The mapping between those filters and the communities, is it static, or how does it work? You have to predefine them,
Yeah.
which filter is associated with which community?
Yeah, yeah.
And
good
how
question.
do you extend it?
Yeah, good question. So it's static. There is a specific static list of action rule to BGP community, which is predefined. And this list has been generated based on the DDoS traffic which we observed over the DKIXs. So we looked into the flow statistics which we do using IPFix on the DKIXs, and then based on that we have seen the most common attack vectors. The team has evaluated that also with other people researching in the DDoS field, what are the attack vectors, and based on that, these rules were created. So they are static, but that doesn't mean that it's the end of the list. So if there should be a new attack vector in the future, we will update the list. And we have in the DKIX portal and then later on also in the SwissIX portal a specific email address where you can also directly talk to the team. For example, in case you should be missing a specific rule, then this can be added. So it's not a finite list, but it's a static list which can be updated on demand. A couple of business days, basically, I would say. It's not something which is very long. Yeah.
Okay, thank you, Daniel.
Thank you as well.